So this video talk raises the question, if a spaceship goes too fast, does it turn into a black hole? This is going to be a short video because I can't find anything decent on this issue. So this is from Britannica. It explains what relativistic mass is. It says in the special theory of relativity, it's the mass that is assigned to a body in motion. So I'll give you a moment to read the equations and so forth. So the important thing that's being said there is the relativistic mass m becomes infinite as the velocity of the body approaches the speed of light. So even if large momentum and energy are arbitrarily supplied to a body, its velocity always remains less than c. So relativistic mass is an idea that was brought in to try to explain why a material body couldn't go at the speed of light. I think I'm explaining it a bit better in a moment. So repeating it again, the relativistic mass becomes infinite is the excuse used to say that an object can't go at light speed c. Light is supposed to have rest mass m subscript 0 equal to 0, so it can go at light speed c, and c is the speed of light in vacuum free of the influence of fields. But material objects have non-zero rest mass, and so their relativistic mass m increases, and so m becomes infinite at speed c, thus can go at speed c. The equation for relativistic mass is shown there. And what is being missed out is, surely if an object goes fast enough, then it will turn into a black hole at a mass less than infinite. So relativity texts don't seem to want to deal with that issue which was just highlighted, and I can't find anything decent dealing with it. Texts are happy to tell you that a material object can't go at light speed c because its relativistic mass would increase to infinite, which would then be deemed not possible. You can't have an infinite mass, so therefore an material object can't go at light speed c. But the texts don't want to touch the issue that a material object at a certain speed less than c would turn into a black hole. So not having a decent source, have to deal with what Wikipedia says. Wikipedia is usually a good rough guide, but isn't 100% accurate. So what follows is going to be a bit vague. So this is what Wikipedia says. The word mass has two meanings in special relativity. Invariant mass, also called rest mass, is an invariant quantity which is the same for all observers in all reference frames, presumably they mean inertial reference frames, while the relativistic mass is dependent on the velocity of the observer. According to the concept of mass energy equivalence, invariant mass is equivalent to rest energy, while relativistic mass is equivalent to relativistic energy, also called total energy. And Wikipedia goes on to say the term relativistic mass tends not to be used in particle and nuclear physics and is often avoided by writers on special relativity in favour of referring to the body's relativistic energy. And my note on that is it tends not to be used because it causes problems, which I highlighted earlier, that if a material body, such as say a spaceship, goes fast enough, then its relativistic mass will increase until it becomes a black hole, surely. Right. In contrast to invariant mass, it is usually preferred over rest energy. The immeasurable inertia and the warping of space-time by a body in a given frame of reference is determined by its relativistic mass, not merely its invariant mass. For example, photons have zero rest mass, but contribute to the inertia and weight in a gravitational field of any system containing them. So this is where you get the, light is a particle, a photon, and it has zero rest mass. And having zero rest mass, it's able to go at light speed. But a material body has a rest mass which is not zero and hence cannot go at light speed. See, this is all their little fiddle they do. So Wikipedia says relativistic mass is not referenced in nuclear and particle physics, and a survey of introductory textbooks in 2005 showed that only 5 of 24 texts use the concept, although it's still prevalent in popularizations. So some relativity textbooks do use the relativistic mass concept. Wikipedia goes on to point out that the relativistic mass concept comes from Tolman, or it seems to come from Tolman, because Wikipedia says Tolman in 1912 further elaborated on the concept and stated the equation there is best suited for the mass of a moving body. In 1934, Tolman argued that the relativistic mass formula, which is shown there, holds for all particles, including those moving at the speed of light, while the formula for relativistic mass only applies to a slower than light particle, a particle i.e. with non-zero rest mass. Tolman remarked on this relation that we have, moreover, of course, the experimental verification of the expression in the case of moving electrons. We shall hence have no hesitation in accepting the expression as correct in general for the mass of a moving particle. So Tolman is claiming experimental support for this relativistic mass, and of course, if you've seen my other videos, I start disputing the interpretation of experiments. Special relativity tries to impose certain interpretations onto experiments, and when you talk about this in physics classes, they don't go into all the possible interpretations which you could put onto experiments, and they just try to impose the dogma of special relativity. In this case, Tolman is stating experiments should be interpreted as having relativistic mass. Wikipedia goes on to talk about popular science and textbooks. The concept of relativistic mass is widely used in popular science writing and in high school and undergraduate textbooks. And then it goes on to tell you that authors such as Ocken and Arons have argued against this as archaic and confusing and not in accord with modern relativistic theory. And so what Arons writes is, for many years it was conventional to enter the discussion of dynamics through derivation of the relativistic mass. That is the mass-velocity relation, and this is probably still the dominant mode in textbooks. More recently, it has been increasingly recognised that relativistic mass is a troublesome and dubious concept. And of course it's a troublesome and dubious concept because of what I've highlighted. Well, if you've got a material object with non-zero rest mass, its relativistic mass at a certain velocity will have turned it into a black hole. It's thus the troublesome concept. So note the bit, authors such as Oakham and Arns have argued against this as archaic and confusing. And in other words, they're trying to jettison the concept. After it was being taught for many years to physics students, suddenly the people who believe in relativity have decided, oh, relativistic mass actually causes problems, so we don't want it in the theory anymore. Now, I've dealt with this paper in a previous video. It talks about two myths about special relativity, and it gives two examples of myths that have been taught to physics students about relativity. Now, in the context of relativistic mass that has been taught to physics students, the relativists seem to now want to say relativistic mass is another myth. So this is what's the changing process going on in relativity. One moment they teach you something, and a few years later on the loud they suddenly decide, oh no, we shouldn't have taught that, it's a myth. So, given relativistic mass, you might expect a spaceship using super technology from a highly advanced alien civilization that as it goes faster, then at a certain speed it would look like a black hole. Those revising relativity don't seem to like that idea and seem to want relativistic mass deemed a myth. And that's the end of this little talk. If I had better sources discussing this idea, I would have given it, but it is a general idea that relativistic mass leads to this problem of black holes. Suddenly, in special relativity, you're not supposed to be dealing with black holes, but suddenly they turn up via relativistic mass. What? You go, what? Something gone wrong here. And they've been teaching relativistic mass to physics students. But of course, when there's a problem in relativity, they try to avoid talking about it. Thank you. The end.